I hope you are doing well. In this lecture, I will cover the how do we write the algorithm build max heap, and then what is the time complexity of this one, right? Suppose we have array. You can see this is the array. It is given. You have to convert this array into max heap. So we have a formula max heapify. You can see we can write is max heapify. So in heap max heapify we pass two things, array and I index. What actually does, it takes I is the what location of any root of subtrees, like this one we have a sub binary tree, right? And what this function actually does, this function repair the subtree to make it as a max heap, right? Max heap properties, if any function any subtree which is not holding the max heap properties will will be repaired by this function, right? Let's see actually what we pass in this I locations. So in the beginning we will pass first 5, then 4 and 3 and then 2 and then 1. How do we actually get these numbers? So if we know this number 5, then it is very easy, 5 4 3 2 1. But how do we get these numbers 5? We as we know, the last location of this whole array is what, a dot size. Hmm? A dot size is for what, 10. And we know, if we want to know, we want to find out the location of this child, then it goes to, we can write 10 by 2. This is the parent of any child of which is present in a dot size, right? A dot size is just nothing, is the length of array, and we can say the last location of elements in the array, right? We pass one by one elements, one by one subtrees. You can see if we pass 5, what it means, we have passed this subtree. If we pass 4, what which means we pass this subtree, this subtree, and this subtree, and whole tree we pass to this max heap, or max heapify will actually as in do sweeping and anything else max heapify will do and prepare the max heap for us, right? As you can see, I have written same things, a size by 2 minus 1, this is the first one, 5 4 3 2 1. These are the I values, right, what we are passing. Let's see how the algorithms actually works. So max cppi, I have written algorithms. What we are passing two things, I have written p here rather than I. What it means, p means parent, right? Or we can say this is the root of the tree what we are talking about, right? So parent has two childs, as we know, left child and right childs. We compute by, if we multiply by 2, what we get, the left childs. If I multiply by 2 plus 1, then we get the right child. And what in the beginnings, what we assume that the parent is the largest one. As we know, we have to, if we find any child out of these 1 and 2, left or right child is larger than this parent, I do swapping. So this is the main main objective of this max cp5 function. So what we will check first, as we know, the size of array is a fixed one, a dot size is a maximum size. As we here multiplying, you can see the with index, so that's why we have to check whether L and R are both are falling within the array. You can see in this two things, two lines we are checking whether the index is falling within the size of array, right? This is nothing. Now we will compare from the parents to left child. You can see, if left child is greater than, what we do, we assume that the largest element is the left one. And what we need, if right child, as I have explained these two things, this and this one, I will we look at that. If is the largest element means right element of the parent p is still greater than the largest. What which one the largest already said by here. Still it is the largest, means large right element. In that case, largest will be updated by r. Just this is nothing, just if we are taking maximum of left child and right child, right? Then if we find these two are, if the largest element has been updated, and what it means, parent is not a largest one, somewhere these two one of or both instructions has been executed. In that case, we do swappings and call for the next one, the largest which was changed, and we do recursively these things. What we get, the at the end we get the you know max heap rooted with p. This is what we do. So let's take one examples. With the help of examples, we try to understand these functions. Suppose we have array, you can see over here 2 is there and 10 is there and 20 is there. At the beginnings, location of this one is, suppose we take p, you can see p is there. If we do 2 to p, what it means, we get location of left child, and if we do 2p plus 1, we get the location of right child. So that's why I have written here L and R, right? I hope this is clear. We check from left childs from of parents. If left child having the larger value than the parent one, then what we do we indicate by largest is a left one. So largest would becomes here left one, and the next iterations what we do here, what will have, we compare even though largest one with right one, means in other word, we are taking maximum of these two childs with parent. If in next case, what will happen, 20 is still greater than of 10, what will the largest will becomes right child. This instruction will be executed. Now what we find, in the beginnings we have assumed that the largest is parent. Now it has changed by executing these two instructions. So we take swapping, we do swapping with what, these two, means with the right child we do swapping, because this instruction was executed, and what it means that largest is now r, and p and r is not equal to, so that's why we do swappings, and then 20 will come here and 2 will come here. So now you see the value at this place has been changed, and you can see this, the value of this place is become larger. So not need to call for this index, we have to call for this index, because the lower value has come here. So that's why we call again for the largest one. This was the largest one which was pointing it out, right? You can see over here. So we call for this one, the same, this for this root of this subtree, and we repeat the same things. And if there is a there is a problems of holding the property of max heap, in that case we do swapping. I hope this is clear. Now we will move forward, then we talk about the build heap properties. So build heap, sorry, function. So build heap function, what actually does, we are calling from with there is one for loop. So for loops is going from I to 1. I is where I is a dot size by 2. As we know why we are taking size by 2, because we are trying to move from 5 to, if we are simply going from this to this, there is no meaning, because these are the leaf node, they don't have any child. So that's why we are taking size by 2. So we start from here, right? We call for each index, as we know, to repair it and to make it max heap. So as you know, we are moving from this in max heap, just height. As we know, we are moving toward the height. You can see if larger version, then this one, then we call for this one, this one, then again it will call, it will go only up to the height. So there will be one place where L and R becomes higher than this size of array, because we are multiplying by 2. So that is the reason it will go up to height of t. So the height of the time complexity would becomes log n. Then we take multiplication of these two, and the time complexity would becomes n log n. Do you think it is correct? No, this is not correct at all. Let's see how it is incorrect. So the time complexity how we compute it is just take multiplication log 2n. No, it is not correct one. As we know, so if we go upward, see, if we go upward, the number of elements are reducing drastically. So this is the main reasons behind this is the main reasons behind the time complexity is not equivalent to as we see theoretically. So we use the mathematical things and find out what is the time complexity of build heap, right? So you can see you can see we have a height. You can see 0 to 3 as I talked in first lecture, and number of elements in any levels, at any levels you can see n by 2 power h plus 1, right? Yet for this levels I have computed n by 2 by 1 plus 1. We have 1 this is the value of h, because height of this tree is 1. So and how many elements at this levels, and we go to a height, right? What is the height of? So let's take one functions where we go to height 0 to log n. We this is the height of this function. So sorry, this binary heap, you can see height of this binary heap is, we are going from 0 to h, right? The number of element at each levels, I am assuming that n by 2 power h plus 1. This is the formula we can get the number of element at any levels. Now we actually the time complexity of this max-heap, as I told you, log n, right? We can write over here, and I have to do say integration for the dh, right? So we can go from 0 to log n, and we can convert into the h, you can see. And if we do integrations, what we get to the value n into minus something value plus constant. In other word, we can say this value goes to constant only. So the time complexity would become just order of n. What we thought here, order of n log n. No, if we do the mathematics, what we get the time complexity order of n. Yeah, exactly order of n only. So where we use this data access main heap or max heaps, there is one abstract data types which we call the priority queue. There we use the main heap or max heap according to our need. Suppose if there is a requirement of frequently needs of main elements from the array or from anywhere, in that case we will use the minimum priority queue. There we can implement as well the max priority max element from the priority queue, or so it depends on our applications. So priority queue is just nothing is abstract data types which uses the max heap or main heap to data structure to build up. So it can provide the decrease key, increase key, the functionalities to the users. I hope this is clear. If you think this lectures is helpful for you, or you find any problems to understand the time complexity of build heap, you can ask me, uh, and you can share with your friend, that will also help your friend. And if you like, then it will help me to motivate such video for you. Thank you for watching.